Okay, welcome to your last video of the year. This is on symmetry and dilations. We're going to start with symmetry in section 9.6. A figure in a plane has a line of symmetry if the figure can be mapped onto itself by a reflection line. In other words, it divides a figure into two congruent parts. We kind of, not really a line of reflection because that was flipping it across something. In a dilation, you've got a line kind of down the middle, and you're going to see whether or not it cuts a figure in half, and it has to be two congruent. So I've got three examples right here. How many lines of symmetry does the hexagon have? Notice all three of these shapes are hexagons. So wouldn't every hexagon have the same amount? No, that's not true. In example A, I can take and draw a line going in this direction. And then if I think about taking this top half and folding it in half, it would lie right on top of the bottom half. So that is one line of symmetry. If I thought about moving it, I can go right down the middle here, and if I take this and I fold it over, again, that's another one. So this particular one has two lines of symmetry. In class, we'll probably get out the patty paper again, because sometimes if you're having trouble seeing them, you can trace this on patty paper and just try folding lines. For example, some people want to try to draw one going this way, but this little piece is not going to match up over here on this piece. So that would not be a correct line of symmetry when I do that one. Okay, so they have to cut the figure directly in half. So that one had two. On B, how many lines of symmetry do I have? Well, I could take and look at it like this. It'll also go that way, and it'll go that way. So right now I have a total of 1, 2, 3 lines. But I can also do like I just did in the last one. I can go that way, which makes 4. And then I can go between these two right here, which makes 5. And then I can go between these two right here, which makes 6. Sometimes you can rotate your figure to help you see where your lines of symmetry is. So this particular example has 6 lines of symmetry. Can you tell me the difference between A and B? Can you give me a special name for the B hexagon that would not be true for the A hexagon? Very good. B is a regular hexagon. And if I have a regular hexagon, any regular figure, the number of sides will always equal the number of lines of symmetry. So if it's regular, if it's 6-sided, it's going to have 6 lines of symmetry. If it's an octagon that has 8 sides, it's going to have 8 sides. On C, the only way I can draw a line is right here. Now, will every figure have a line of symmetry? No, and we'll kind of look at that in class. So lines of symmetry cuts a figure basically into two congruent parts. Okay, now that we've finished the line of symmetry, we're going to talk about rotational symmetry. If the figure can be mapped onto itself by a rotation of 180 degrees or less about the center of a figure, then it has rotational symmetry. The center of the symmetry is the point on which a figure is rotated. So when we did rotations earlier, we did it about the origin. So now what we're saying is the center is going to be the point that it's rotated about, and rotational is when you rotate it about the center of the figure. So we're going to look at 3 different types of rotations: a parallelogram, a regular octagon, and a trapezoid. Okay, so sometimes some figures will have multi-rotations. You never want to give us a degree over 180. So I've got my parallelograms, they're pretty well lined up. Center rotation means I'm going to think about taking and right there about would be my center, and I'm going to rotate my figure about that center. So I'm going to take my parallelogram and I'm going to turn it. So I'm turning it. That pretty much is a 90-degree turn because I did like one time. Then I'm going to turn it again, and that's my 180-degree turn. And notice how I'm back right where I started on the parallelogram. So a parallelogram has 180-degree rotation. And that was the only time that the parallelogram went back on itself. So the parallelogram has one of them, and it is 100, 180 degrees. Now I'm not going to take the time to take my regular octagon and draw it and flip it and rotate it and stuff, but on a regular octagon, anytime it has that word regular in it, then regular means that it's going to spin around as many times as there are sides. So the whole way around is 360. So I take 360 and I'm going to divide by 8, which gives me 45. So my regular octagon at 45 degrees, I will line back up, add 45 and 45, and I get 90. So at 90 degrees, I'll line back up, add 45 to 90, and I get 135 degrees. So at 135 degrees, I'll line up, add 45 to 135 degrees, and I get 180 degrees. So this time, there are 4 different places that it would line up. When I turn the regular octagon, it would line up with the original octagon at 45 degrees, 90 degrees, 135 degrees, and 180 degrees. So now I have my trapezoid, so I'm going to start turning my trapezoid, and when I turn it, don't mean to make it a different size, there's 90 degrees, there is 180 degrees, and notice when I turn it, it's not going to line back up with itself. So on a trapezoid, there is no rotational symmetry, because when I turned it 180 degrees, it never landed back on top of itself. So the one trapezoid did not cover the other one. So in a trapezoid, you have no rotational symmetry. Now we're going to look at dilation, section 6.7 in the book. A dilation is a transformation that stretches or shrinks a figure to create a similar figure. So unlike our reflection, our rotation, and our translations, these are not isometric, okay? They do not hold their congruency, but they are now similar. So everything we learned in our unit on similarity would apply to dilations. The center of dilation is the point in which a figure is enlarged or reduced. So you can take a certain point and enlarge it or reduce it from that point. That is called the center of dilation. We're going to pretty much look about the origin. We've talked about scale factor before. It is the ratio of a side length of the image to the corresponding side length of the original figure. We use the letter K to represent scale factor. Now we had a little bit of difficulties in our other classes because the book kind of said one thing. Here in this chapter 2, in this chapter 6, it finally says it is a ratio of side lengths of the image to the corresponding side length of the original figure. And when you take your SAT or your PSAT or any other standardized test, that's the definition you need to use whenever they say the word scale factor. How big did it get or how small did it get? We've done coordinate notations for reflections, rotations, and translations. So now we're going to do them for a dilation. A dilation is just making it bigger or smaller. So our rule just says xy goes to kx, comma ky. That is our new point, whatever we're multiplying by. So if we are doubling a figure, k would be 2. So xy would go to 2x, comma 2y. So we just multiply by the figure that it's going to go to. Now, if k is between 0 and 1, then the dilation is going to make the figure get smaller. It's going to reduce it. If k is greater than 1, then the dilation is in enlargement. We won't get into what happens if k is negative because that just does some weird things and we're not at that point. So our k's will be positive. And so there, for a reduction between 0 and 1, for an enlargement, k has to be greater than 1. Okay, draw a dilation with a scale factor greater than 1. So we're going to plot A, B, C, D with the vertices that are given, and we're going to use a scale factor of 2. So pause the video and plot your 4 points. Okay, I plotted my 4 points, my A, B, C, and D. Now I'm going to use my scale factor, so I'm going to go ahead and find A prime. A prime says I multiply everything by 2 for my scale factor. So 2 times 2 is 4, and 1 times 2 is 2. B prime, I take 4 times 2 is 8, and 1 times 2 is 2. C prime, I take my C point. 4 times 2 is 8, and negative 1 times 2 is negative 2. And finally for D, 2 times 1 is 2, and 2 times negative 1 is negative 2. I'm going to plot those points. So at A moves to 4, 2. There's my new A. B moves to 8, 2. So there's my new B. C moves to 8, negative 2. There's my new C. And D moves to 2, negative 2. There's my new D. Now remember, since this is the image, I need to put the prime notation marks on there as well. So here is my new figure. It's still a trapezoid. It's just gotten bigger. Notice my points all moved because I'm doing it about the origin, which is about this point right here, which is going to cause all of them to enlarge because I'm going with a number greater than 1. Okay, now we're going to look at a dilation that is less than 1 and also talk about how to verify that it is similar to the dilation. So once again, pause and plot the points. I plotted my triangle ABC. So now I'm going to have to find my A prime. So I'm going to take that point 4, negative 4, and I'm going to multiply everything by a half. So half of 4 is 2, half of negative 4 is negative 2. My B prime, 8, 2, half of 8 is 4. And half of 2 is 1. My C prime, half of 8 is 4, and half of negative 4 is a negative 2. So now I'm going to plot those points, 2, negative 2. So there's my A prime. B is at 4, 1, so there's my B prime. And C is at 4, negative 2, so there's my C prime. Now, when it says verify, remember this time we're talking similarity. There's only 3 choices for similarity: side, angle, side, 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 or angle, angle, angle. Well, I can figure out one of my angles. I know that both of these angles right here are 90 degrees because it's vertical and horizontal lines, which are perpendicular. So I've got one angle. But I don't know how to verify for the other 2 angles, so this method right here would not be a good choice. So I can do side, 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 or I can do side, angle, side. Notice that the side over here is 2. This one has a length of 1, 2, 3, 4. I can count because they're horizontal. I'm going to count my other vertical, 1, 2, 3, 4, 5, 6. And my other vertical over here, 1, 2, 3. So it has a side length of 3. Remember, when we're talking about sides, they don't have to be congruent, they have to be proportional, and I need to go between triangles. So my vertical line of 3 compares to my vertical line of 6. And I know I put the smaller one on top because the red one was my image, and it's the image to the pre-image. Plus, I know I have the smaller one on top in order to get a 1/2. And then I do the other one, which the other one is what corresponds to the smaller triangle would be 2 compared to the 4. And when I reduce both of those fractions, I get 1/2 to 1/2. So therefore, I've now verified that it is a similarity by my side angle side property. I could do side, side, side as well. That means I'd either have to use Pythagorean theorem or different distance formula to find A prime, B prime side, and distance formula or Pythagorean theorem to find the AB side, and do side, side, side. That is the end of our dilation video. I hope you enjoyed.